Okay, Assalamualaikum and good morning. So today we have uh, this lecture to do. So let me go to the notes. So can you see this? Right. I will begin with the lecture, but I will have to say something about tomorrow's test at the end of the lecture. So please stay with me. So so today we have actually done in the previous lecture regarding how to describe Maxwell equation uh, in terms of the field strength tensor and also the gauge. So we have not quite sort of touched upon the transformations available for uh, the physical concepts inside such a theory. So today we'll do that. So there are essentially two types of. Can you actually see the cursor? Somebody?
Yes.
Yes. Okay. Good. So then I don't have to scribble too much. So there are two types of transformation uh, for the theory. Essentially, one of the things that we already learned much earlier is that there will be Lorentz transformation. Okay. And then the other one would be the gauge transformation we just introduced when we try to solve equation. Okay, so these two, in a way, sort of intertwine with each other. Okay, so we'll look at this in a minute. So so let me just introduce the gauge potentials earlier. We have the vector potential, okay, and then the scalar potential, and they form a four vector. Okay, form four vector, and essentially these are not unique to a particular E and B. Okay, because you can do gauge transformation that gives you equivalent E and equivalent B. You can just refer to the previous notes or lectures. So what are the gauge transformations that's available for the vector potential? You can actually define it up to a gradient of scalar. Okay, scalar being psi over here, and then for the scalar potential, then one needs to so simultaneously have this change. Uh, the transformation is the change of psi with respect to time. Okay, so if we look at what this is a spatial derivative. This is the, the, the time derivative. Okay, the time derivative. So it's the fourth component. So one could actually write sort of more in a more condensed manner that this both the derivative comes from the four-dimensional derivative. So which is this one. So let me remind you again that this is meant to be d psi dx mu. Okay. So okay, and then one of the things that we did was to see how well the gauge sort of fits into the Maxwell equation. There are two Maxwell equations that we're looking at: the source-free, and then the you know, the source equations. Okay, so one of the conditions that we need to make to simplify further the equations is that input kind of Lorentz gauge condition. So the Lorentz gauge condition is given by this I call in terms of, okay, recall Lorentz gauge condition is given in terms of the Lambert of your uh, introduced scalar function. Okay, so this is just similar to what we seen before. So this is just that. Okay, so that, if you remember, you can actually write a kind of a wave equation for this. So that wave equation is given by that, and if you make this, okay, this which just correspond to this, okay, to be the negative of, okay, then you have the Lorentz gauge condition. Okay, so let's check. So the Lorentz gauge condition, look at what it is. Uh, on the left hand side, for example, you see that this index is contracted with this index, okay, and then on the right hand side is the same. So in other words, when it's contracted, this is a scalar equation. Okay, so it's a scalar equation, and one of the things that we know in special relativity is that when you have scalars, their properties doesn't change under change of reference frames. Okay, so that's good. In other words, there are no components like the vectors or tensors, but they are just given a particular point, they are just pure numbers. So the pure numbers will appear the same in all reference frames. So in other words, this equation, this Lorentz gauge condition, once you fix in one frame, you will find that this will be valid in other frames as well. Okay, so that's the main idea. So that is in terms of the potential, but let's recall that the potential is not unique. Okay, the gauge potential, the A mu, not unique. Okay, the one that's actually unique as a physical quantity is essentially your electric field and magnetic field, and these are conveniently what you call described by your field strength tensor, which is now written as F mu nu. And let me just remind you, which is going to be relevant for the test 2 tomorrow, okay? Because these are tensors. You have done how tensors transforms. So there are several ways to actually encode this idea of electric field and magnetic field. The one that we normally introduce is this covariant tensor, but you can also have the contravariant tensor, okay, and the other thing that we also introduce is the idea of a dual tensor, okay. These are actually done much earlier when we introduced tensors, okay. So but all these four are equivalent, sort of equivalent ways of describing your electric field and magnetic field. So you have options how to actually write them. And there are tensors, so tensors will have will obey some form of transformation law under special relativity. Okay, and these are given by the Lorentz matrices, for example. Okay, so for each index there will be a Lorentz matrix. Okay, multiplying, sort of contracting with these indices on the field strength tensor to give you the field strength tensor in the new frame. Okay, so the one without the dash is the old frame, and the one with the dash is in the new frame. Okay, similarly for the covariant case. Okay, so the covariant case will involve what we call the inverse Lorentz transformation. So I hope you still remember why we have the dash. Okay, the dash are just like using a different coordinate system. So let's mu dash as functions of the old one. Okay, and this is just the same thing as if we introduce y mu instead of x. Okay, so this is probably a much more relatable things like you write functions of x as f, for example. So this would be the symbol, but we do not want to introduce too much in this because we want to focus on the indices so that you know what is a tensor, what is a scalar. Okay, so that's essentially the lesson that we should learn from much earlier lectures. Okay, so now essentially we have this so-called transformations for the case of the field strength tensor, which we must take note of. Okay, particularly what we want to do is the case where when you go to a different frame, the different frame is actually related to the case of the Lorentz boost, meaning going from a stationary frame boosted into a moving frame with constant velocity. Okay, so let's consider a particular case, the case of the Lorentz boost transformation in the x direction. So if we go back to the lectures on transformation, we know that, okay, again, let me just remind you of some things that I found in test 1, which you have to be careful about it. I've not been strict in terms of my marking, but perhaps again, one should remember this pretty well, and then that shows some understanding. Remember the first row, say, let me just number the rows 1, 2, 3, 4, and then the columns 1, 2, 3, 4. Okay, recall that the first 3 rows or the first 3 columns correspond to what we call the spatial indices, like x mu is x, y, z. Okay, for the x1, x2, x3, and the fourth component is the time one. Now I see some answers in the first test where you use a different conventions and then which I still accept. Okay, because it depends on the context. Okay, if I ask you specifically to write with a specific convention, then you need to answer that. Okay, so please take note of that. Okay, sometimes the convention adopted in different books will be different. Okay, so mine is actually using 1, 2, 3 for the spatial index, and the fourth is the time index. Okay, and then when I recall, for example, an answer that I find quite amusing is when I asked you to do Lorentz boost in y direction. So you swap between x and y. Of course, that gives you the right answer, but then one has to maintain that swap. If it's a long calculation, you have to maintain that y appears before x all the way through the calculation. So in calculations, always be consistent with respect to this convention. Otherwise, you get nonsensical results. Okay, so I'm just giving some of what my observations are from your previous tests. Okay, I will talk more about this at the end of the lecture. Okay, so now what we have essentially this Lorentz transformation is sort of change the components of your tensor for your electromagnetic field. Okay, and that also tells us about how electric fields and magnetic fields change under change of reference frames. So this is a much more physical thing to do in this particular context. Okay, so let's look at one of them. Let's look at say, remember, I don't have it over here. Maybe I'll open up previous lecture, I suppose. See, send this. My right click is not happening. Bear with me. Somehow I have problem with my laptop here. Oops. What lecture was that? Lecture 14. So I want lecture 13. Just to remind you. Okay. Yes. Okay. So let's just recall my let's have it somewhere here. Oh yeah, okay. So let's recall this, for example. Okay, and you can see, for example, over here. Again, this is very much more important now because it will tell us which one is the electric field and which one is the magnetic field. So if you jumble up the convention that I mentioned earlier about 1, 2, 3 being spatial and 4th being the what we call the sort of the temporal index, you might get this looks differently. Okay, so this whole field strength tensor will look different when you use different convention. So that's why now in this particular context, it's much you must be more cautious about what conventions you adopt and not just simply take from some sources without understanding the conventions. Okay, so over here, for example, let me just point out, I can take this component. So what is this component? Is essentially the first row and the 4th column. So that is F14. So we are going to look at F14 component of your field strength tensor. So let me go back to the previous lecture, the lecture 14. So what we want is to look at, say, F14, okay, and how it transforms. Okay, so F14 corresponds to the first component of electric field. Okay, so just plugging into this equation over here. Okay, so I have one mu dash over here to be 1 dash. Nu dash over here is actually 4 dash, and so you just plug those values in on the right hand side. So I have mu dash to be 1 dash, nu dash to be 4 dash over here, and then we have the dummy index, rho and sigma, that stays as it is at the moment, and we'll try to see how to sum this. So remember, this will be summing over all indices, say rho's and sigma from 1 to 4. Okay, I'm showing this explicitly so that you know what to do when you see a question with respect to this. Okay, so you have to sum over all possible cases. So there will be what? How many terms will there be? So for each index, there will be 4 terms. Okay, so that means 4 times 4, there will be 16 terms. But of course, not all 16 terms will be non-zero. In particular, we look at this case of the Lorentz boost. So the Lorentz boost has non-zero components in the first column and the fourth column, and zero elsewhere. Okay. So the same thing here. The fourth in the fourth row, there will be the first column and the fourth column. So the index over here that one should be more concerned of will be the indices of 1 and 4. So let's just look at this. So if you look at from the previous description that we had, your rho and sigma, you focus on rho and sigma when rho and sigma is 1 and 4. Okay. The rest, for example, what's going to happen? Let's say 2 and 3. What's going to happen for the case of 2 and 3? Then essentially, what do you have? L to 1 dash. L to 1, oh, I'm looking at this one. L to 1 dash would be row 2, column 1. Okay. So that's not going to work. But what about the case of rho equals to 2, sigma equals to 2? Then this will be simply to be, let me just write it down. So if I take L to 1 dash, L to 4 dash. Okay. Then again, if you look what the matrix entries for this Lorentz case, L2 1 dash is 0, L2 4 dash is also 0. So in other words, because of these indices over here, you find that, okay, it must match with this index for this particular transformation. So it's either, so both of these are zeros. Okay, let me just write that down. So you must have either L, let's just take this one, 1 dash. You must either have L1 dash 1, okay, in this particular case would be gamma here, or L1 dash 4, and that would be gamma V on C. So if you put this in, then you have the following. Okay, so you have that is just for one what you call one of these index. So you remember you have two Lorentz inverse Lorentz matrix over here. So you have to make sure that you contract with the right one. Okay. So here, for example, L11 dash, L44 dash. And essentially that gives you a rho with 1, rho is 1 over here, sigma is 4. Okay, and then we do the other one. Okay, so remember over here we had 1 dash with 1, so the next thing is to have 1 dash with 4. Okay, so L for 1 dash, L11 dash, F41. So now we plug in what this is supposed to be. F14, remember, is your first component of your electric field. Okay, just like this one. Okay, but what is F41? Well, you can go back and check your previous matrix if you want to. Okay, F41 is this one. Okay, again, it's actually the first component of electric field. Okay, but you can immediately know that easily from this identity. F41 equals to minus F14 is equals to minus F41. Okay, so you plug those in, but now you have to remember that this also has certain what you call quantities there. L11 dash, let's look at that. L11 dash is gamma, and then L for 4 dash is also gamma, so you get gamma squared. Okay, and then what is L for 1 dash? L for 1 dash is this one. So L for 1 dash is this one. Okay, I think this must be, oh, again, that's a mistake. This would be 4 dash. Okay, remember it's 1 dash, 4 dash. Sorry about that. So L14 dash will be this one. So you have gamma V on C, the whole thing squared. Okay. So you plug those in, and essentially what do we have? Well, gamma squared, if I write this, remember there's a minus sign here, so I pull out your common factor of E1 to outside here, and then this would be 1 times minus V squared on C squared times gamma squared. Okay, so you have that. But what is gamma squared? Gamma squared is simply 1 over 1 minus V squared on C squared. Okay, gamma is 1 over square root of 1 minus V squared on C squared. So in other words, you get gamma squared cancelling this, and you just go back to the point of having your first component of the electric field. Okay, so in other words, your components of your the first component of the electric field does not change under the Lorentz boost transformation in the x direction. Okay, so so that's not so interesting then. Okay, your electric field doesn't change, but let's look at the other components. So that is the first component of your electric field. Now let's look at the second component of the electric field. So let me just go back to the matrix earlier. Second component of electric field is actually here, and this is F24. Okay, so let's look at F24. So we want to see F24 in the new reference frame under Lorentz boost in the x direction. Okay, so again, using the transformation law for the tensor, you have L rho 2 dash L sigma 4 dash times F rho sigma. Again, this will be sum. This dummy index will be sum. And again, we use the observation that we had earlier. Your rho and sigma must match the indices at the bottom. Okay. So what do we do over here? Then you just consider rho and sigma to be either 2 and 4. So you can see that it can be written in this following step. I think what happens over here, let me just see. If I put rho equals to 2, I will get L to 2 dash, and then I would have to have let me think properly at the moment. What's happening here? Oh, okay. This is slightly different from the one above. Sorry. Okay, let me do this systematically. So again, we want to have, I think there's something wrong here. L2 dash 4 dash. I should be having, okay, maybe I should rewrite this again. So I should be having L2 to dash L4 F44 dash, and then this will be F24. I don't know why I'm having this. And then the other one, but that will not work. Okay, I want to have this. Let me try to think what's going on. I would have to have that. Okay. L22 dash, right, okay, L22 dash is that one there, and then this will have to be contracted with F2, and then I need to determine what this one is. Let me work this properly. Let me go to the whiteboard. L row 2 dash F. Okay. Sorry about this. I was not focusing this part earlier. L 4 dash F row sigma. Let me write this in full so that you can actually see what's going on. So I should be having all the right indices over here. Okay, if I put rho equals to 1, L12 dash is going to be 0. Okay, just look back over here. L12 dash is going to be 0, so I don't want that. So I will have that with L22 dash. And for this one, L4 dash, so what is non-zero in that particular case? L4 dash, so I need the fourth column, right? Fourth column. Right. So the fourth column, I have the option of taking this one. No, okay. I should have done this more systematically than what I said. So at the fourth column, I will have the non-zero elements to be at row 1, sorry, at first row and the fourth row. Okay, so let me go back here. So that means that gives it us 1. So what I mentioned earlier, it's not quite correct. Okay, so you really have to look at the Lorentz matrix itself. So it doesn't really have to match the one at the bottom. Okay, you go back to what the Lorentz matrix looks like, and then see what the non-zero one, non-zero elements for your this is 1, this is 2, right? So this is F21. Okay, and then what's the other one? Let me go back. So L22 dash L14 dash, and then L22 dash L44 dash. Okay, so that gives me over here gives you F24. Okay. Now you might ask, what about the other possibilities? Recall that this is from the case of 2 dash over here. So the 2 dash tells you the second row, so the second column. So the second column, the only non-zero case is the case when you have the second row. Okay, so that sort of fixes our possible choices over here. The only choice that's left is coming from this. Okay, now what is, so I look at this, so there is the fourth column. So if I look at the fourth column, then my choices are going to be the first row or the fourth row. So this the earlier case was just a coincidence. For each of these components, you have to check individually. Okay, what's inside this Lorentz inverse Lorentz matrix. Okay, so that settles that. So if you look back over here, you'll find that your L22 dash is a common factor. So you just have that plus L44 dash. Okay, so that settles that problem. So now we have to find out what F21 and F24. So let's go back to that matrix earlier. F21, F24. So F21 would be this one. This is F21. And F24 is this one. Okay. So what we have in this particular case, sorry, I'm supposed to go back to this one. So what we have over here is F21 will be minus, it's not moving. Okay. F21 is your minus B3 over here, and F24 is your E2. Now something is now beginning to look different from the one earlier. The earlier one is that your first component of electric field does not change under change of reference frame. Okay, but over here you find that you have E2 and also B3. So it requires a magnetic field component. Okay, and for the coefficients over here, L14 dash, if you go back up, L14 dash would be this one. So you get gamma V on C times minus B3, and then L44 dash would be gamma. Okay, so you get that. Okay, so this looks different from the one above. Okay, so here you get your second component of electric field acquires a magnetic field under the boosted reference frame. So you can check, so this is an exercise, you can check also for your third component of your electric field, it acquires a magnetic field component, which is given by B2. Okay. So, okay, so that is for the, so you have all the electric field components now. So you have E1 dash and E2 dash, and then you have your E3 dash. Let's just proceed, and then we go back to sum up what we have actually found. let's proceed for the case of the magnetic field, say the first component. Okay, so if you look at where is the first component appears, the first component appears in the second row, third column. Okay, so you need F. So let me just write that, F 2, 3. Okay, so in this particular case, you have F2, 3 here. Okay, so again, we use the Lorentz transformation there. So you have fixed the indices to be 2 dash and 3 dash over here. So you have L rho 2 dash, L sigma 3 dash, and then contracted with F rho sigma. Okay, again, I should be careful what I'm saying now. So you go back to the Lorentz matrix. Go back to the Lorentz matrix and see what possible non-zero values that you should have. Okay, so I'm not going to go too deeply now. You just look at the appropriate rho and sigma which is non-zero. So in this case, will be just L22 dash and L33 dash. Okay, and L22 dash is just 1. Okay. L22 dash is just 1, and then L33 dash is just 1. Okay, and that gives you again, okay, the first component of your electric field doesn't change. Okay, that's not so interesting, but let's look at the other components. For B2, second component of magnetic field, second component magnetic field appears here, for example. So this is F31. Okay. F31, so let's do that. So you have F3 dash 1 dash. So on the right hand side you have your Lorentz matrix fixed by this indices 3, 1, 3 dash and 1 dash, and then you have your dummy index again, rho sigma, F rho sigma. Again, one has to be careful where, let's look at the first Lorentz matrix, inverse Lorentz matrix here. So the only non-zero case will be coming from the diagonal ones. Okay, this one. So, and then for the other one, so this is more or less fixed. Okay, the other one, 1 dash, that means the first column. So the first column will have non-zero elements on your first row and also on your fourth row. So that's why you have L11 dash here and L41 dash here. So that means over here you have 3, 1 correspond to this, and over here you have 3, 4. Okay, that's good. So L11 dash is gamma. Okay, and L41 dash is gamma V on C. So you'll be able to get this equation. So in other words, your magnetic field component in the y direction in this particular case will acquire an electric field. Similarly, if you do for the third component, you'll get your component of magnetic field acquires an electric field under Lorentz boost. So what's actually is happening? So let's sum up what we did. Remember, the one that doesn't change seems to come from the first component. Okay, the first component, and for E, and first component for B. And what does that actually say? The first component corresponds to the x direction, and the Lorentz boost is actually in the x direction. So whatever components of your electric field and magnetic field in the direction of your boost will not change. But the one orthogonal to it, which is in this case y and z, coming from second component and third component, will acquire in this case for electric field, will acquire the magnetic field components. And similarly for the case of magnetic field, it will acquire your electric field. Okay, so these are something that you actually, if you look at what this implies, it's just like, if you move a wire inside a magnetic field, you remember all this high school physics, then it creates a current. Okay, and then if you cut across an electric, if you move, in the case of the electric field, just trying to go back to high school physics, you have an electric field moving, then that somehow, I'm thinking of an example of the high school physics, that will create some kind of magnetic field. I can't remember how. Okay. But never mind, you can check those from your high school physics, and that's essentially tells us all this idea of Maxwell equations from your high school physics point of view actually is embedded inside this Lorentz transformation for your field strength tensor. Now I think I will continue this next week for the more generalized case, because I want to say a few things about the first test. Okay, as I said, in your in your second test, that's what I mean. Your second test tomorrow, please do remember that you have already your assignments, but your questions for your test will be slightly different from your assignments. So please take note of that. So because if you just reproduce the assignment solutions, I'm not testing you. Okay, so it requires you to understand the solutions to approach the test questions tomorrow. So in other words, be conscious of what you're doing. Okay, so it's not just reproducing the assignment question. The other thing, because it's going to be a bit more involved, okay, so you probably require more time. So that's you need to focus on what to do tomorrow. So let me just mention this. There will be something with respect to the Lorentz transformation in a way of remember the scope of your materials that for your second test involves the idea of what you call the classification of four vectors, okay, and then how they can be actually behave under Lorentz transformation. So I hope that's hint enough. And then also for the case of your field strength tensor, okay, there is a question for you in the assignment, but in this test question it's slightly different, but again the idea is to test whether you understand the solutions or not. Okay, there'll be section A, section B. Okay, the section B will be the longer questions. Section A is more towards your understanding. Okay, meaning they might be totally different from your assignment questions. So I'm telling you this because I do not want you to feel surprised tomorrow, and once you're surprised, you panic, and then you don't have time to actually finish your questions. Right, is there anything, I will stop now. Is there anything that you want to ask me for tomorrow?
Could I ask the question about the solution of question 5 in assignment 2?
Question 5 in assignment 2. Okay, let me have to have a look. I'm sure you want to look at this, right? Assignment 2, question 5. Okay, let me just open the PDF. Yeah?
So, Doctor, the question states that if UA is a unit time-like vector, so that's why for the first line you wrote UA equals to 1, right? However, if you scroll down, could I ask?
Which page?
Sorry, scroll up.
Scroll
Doctor,
up.
could I share my screen? I feel like it would be easier.
Okay, then I have to unshare it. Okay, go ahead.
Doctor?
Okay, can you enlarge it for some reason?
For question 5, it states that it's a unit time-like vector. Could I ask, Doctor, how could we get this expression? Because if we're following our...
Can you enlarge that? Because my eyesight is not very good at the moment. Yeah.
If we were to expand this part, wouldn't we get u1 squared minus u4 squared equals to 1 instead of this part here?
I guess so, because I probably have mixed two different conventions there. So again, yeah, it should be u1 dash squared minus u4 dash squared.
So this one should be u1 squared minus u4 squared, right?
Yeah.
Another question is for this one. So I assume this is the Lorentz boost in the x direction.
Yeah.
This one. So, but then according to lecture 4, the Lorentz boost. Yeah, over here it says that it's this expression without the negative on sine h and this on these two terms. Whereas for the solution here, it's given with the negative here. So, like, which expression should we follow?
Okay. Okay, I have not actually checked this calculations. I will have to redo this. I can't. Let me just. Okay. What I'll do is probably I will redo this and then probably upload it again for you, because I cannot do it spontaneously in this particular case. Okay. So probably I have been mixing up two different. No. Those. The kind of questions I often take it from some books. Okay, I'm not sure which book, and they might use a different convention, so got myself mixed up with that as well. Okay, so this is again the reason why I use a different convention is because I'm using the ones that I've been taught with. Okay, so again this actually has been a confusing part of some, with students with the relativity subject. Okay, but it's a good way also to introduce you. There's the various ways of writing it down. Okay, so I'm doing it if you look at most books, they tend to use a different convention. Now, they are most probably because they are written by particle physicists instead of relativists. So relativists is always use the one that I'm using in the lecture notes. Okay, so I will check that question 5, is it? Okay, I'll check this and I'll WhatsApp in the group later on. Okay. Any other questions for tomorrow? So let me get the attendance. Okay. If you have any questions, just WhatsApp me. I may have delays because I don't want to get bothered by too many messages. So if you do have an urgent thing, just WhatsApp me inside the group. No, it's good to do that rather than individually so that everyone is aware of what's happening rather than you alone. Okay? Okay, so if there's no questions, I guess I will end the lecture today. And good luck for your test tomorrow. All right. Bye, everyone.